March 17, 1945. Okinawa Prefecture, southern Japan. In a dimly lit basement laboratory beneath the Imperial Navy's Technical Research Institute in Yokosuka, three men in white coats hunched over a steel examination table. The air smelled of solder and burnt metal. Outside, the city trembled under distant B-29 formations, but inside this concrete bunker, time had stopped. On the table, arranged like artifacts from an alien civilization, lay 17 fragments of American anti-aircraft shells, twisted shards of brass, copper wire thinner than human hair, microscopic vacuum tubes no larger than a fingernail, and components so delicate they seemed to belong in a watchmaker's shop rather than inside an artillery round. Lead engineer Takeshi Nakamura held a magnifying glass over one fragment, his hand trembling not from fear of the bombs above, but from the realization of what he was seeing. For 8 months, Japanese aircraft had been falling from the sky before their pilots could even see the explosions. Zeros disintegrated mid-approach. Betty bombers erupted into fireballs 300 meters from their targets. Kamikaze pilots who had steeled themselves for a final collision with American steel never reached the ships they had vowed to destroy. Their planes simply came apart in empty air as if swatted by an invisible hand. The fragments on this table held the answer, and the answer was terrifying. The Pacific War had become a mathematician's nightmare for the Imperial Japanese Navy. By early 1945, Japan's Naval Aviation Corps had lost over 14,000 aircraft, not merely to superior American fighters or overwhelming firepower, but to something the pilots couldn't understand and the engineers couldn't replicate. American warships had developed an uncanny ability to destroy incoming aircraft before visual contact. Traditional anti-aircraft doctrine required gunners to estimate an aircraft's speed, altitude, and trajectory, then fire shells timed to explode at a predetermined distance. It was geometry rendered in steel and cordite, and it required extraordinary skill. A competent gunnery crew might achieve a 3 to 5% hit rate under ideal conditions. But starting in early 1943, something had changed. American destroyers and cruisers began swatting Japanese aircraft from the sky with mechanical precision that defied probability. Pilots reported shells exploding directly alongside their wings without any visible impact. Bombers flying in formation watched their wingmen vanish inside spheres of shrapnel that appeared to know exactly where the aircraft would be. The kill rate had increased from 5% to over 70% in some engagements. Japanese Naval Command assumed the Americans had simply gotten better at gunnery, more training, more practice, the usual incremental improvements of industrial warfare. But Nakamura and his team had suspected something else. They had been collecting fragments from crashed aircraft, downed planes salvaged from shallow waters around Japanese-held islands, and unexploded shells that had malfunctioned before detonation. And now, on this March evening, they had finally assembled enough pieces to see the pattern. What they saw challenged everything they understood about the limits of wartime engineering.
The fragments told a story that seemed impossible. Each anti-aircraft shell, fired from 5-inch naval guns at speeds exceeding 2,000 feet per second, contained a self-contained radio transmitter and receiver no larger than a cigarette pack. As the shell screamed through the air toward its target, the transmitter broadcast radio waves in a narrow beam. When those waves struck a solid object, an aircraft fuselage, a wing, an engine cowling, they bounced back to the receiver. The shell measured the time delay between transmission and echo. When that delay dropped below a critical threshold, indicating the target was within lethal range, a tiny electronic switch completed an electrical circuit. The circuit triggered the detonator. The shell exploded. All of this happened automatically, without human intervention, in the microseconds between leaving the barrel and encountering the target. The Americans had taught their bullets to think. Nakamura set down his magnifying glass and looked at his colleagues. None of them spoke. They understood immediately what this meant. The United States had miniaturized radio technology to the point where it could survive the 50,000 G acceleration of a naval gun firing, function reliably at altitudes up to 30,000 feet, operate in temperatures ranging from -40 to +100 degrees Celsius, and make life or death decisions in milliseconds, all inside a package small enough to fit inside an artillery shell alongside the explosive charge. Japan's entire radio industry couldn't produce a vacuum tube that wouldn't shatter under such conditions. Their most advanced radar systems required truck-sized generators and teams of technicians, and the Americans were mass-producing this technology, firing it into the sky by the thousands, treating each shell as disposable ammunition. The path to this realization had been long and littered with Japanese dead. The weapon's first appearance came during the Solomon Islands campaign in January 1943, though Japanese forces didn't recognize it immediately. During the Battle of Rennell Island, Imperial Navy bombers attempting to attack American transports found themselves flying through curtains of precisely timed anti-aircraft fire. Pilots reported shells that seemed to explode at exactly the right moment, not too soon to waste shrapnel in empty air, not too late to pass harmlessly behind the target. 8 bombers were destroyed in the first attack wave, an unusually high loss rate, but not unprecedented. Naval Command attributed it to improved American gunnery training, but the pattern repeated. During raids on Guadalcanal, New Georgia, and Bougainville, Japanese aircraft began suffering catastrophic losses to anti-aircraft fire before ever reaching their targets. The pilots who survived, and there were fewer of them each month, described a new kind of hell. Shells that followed them through evasive maneuvers, explosions that appeared directly alongside their cockpits as if magnetized to metal, formations that simply disintegrated in mid-air, 5 or 6 aircraft exploding simultaneously inside identical spheres of shrapnel. The veterans began to whisper about American magic, about bullets that hunted. The younger pilots, already facing near-certain death in a losing war, added this new terror to their catalog of fears. They had expected to die fighting enemy fighters or ramming ships. They had not expected to die alone in empty sky, killed by a shell that seemed to know they were there. Japanese intelligence services scrambled to understand. Captured American documents revealed references to VT fuses and proximity detonators, but provided no technical details. Naval observers watching American ships through periscopes reported no obvious changes to anti-aircraft gun systems. Same 5-inch guns, same radar directors, same fire control systems. Whatever the Americans had invented, it was hidden inside the shells themselves. Retrieving intact examples became a priority. Japanese submarines prowling near American naval formations were ordered to surface after engagements and collect shell fragments from the water. Salvage teams dove on crashed aircraft in shallow lagoons, searching fuselages for unexploded shells. On islands where American and Japanese forces fought in close proximity, combat engineers braved minefields and sniper fire to recover dud ammunition from failed attacks. The fragments were shipped back to Japan in submarines, carefully wrapped in silk and cotton, treated like sacred relics. Because that's what they were, technological relics from a more advanced civilization. Proof that Japan was fighting an enemy that operated on a different industrial plane. Each fragment that arrived at the Yokosuka laboratory added another piece to the puzzle. Nakamura's team worked with jeweler's tools and microscopes, photographing every component, measuring every wire, testing every material. The vacuum tubes alone represented a marvel they couldn't replicate. American engineers had reduced the standard radio tube, normally the size of a thumb, to components barely visible to the naked eye, and then hardened them to survive artillery acceleration that would turn a human body to pulp. The copper wire was wound in coils, so precise that each turn sat within micrometers of the next. The battery that powered the system was a chemical miracle, providing stable voltage despite the shock of firing, the cold of high altitude, and the violent rotation of the shell in flight. But the true genius lay in the integration. Each component had been designed not in isolation, but as part of a system where size, weight, durability, and function had been optimized simultaneously. The radio transmitter broadcast at a frequency that wouldn't interfere with the ship's own radar. The receiver filtered out noise from the shell's own rotation and the electromagnetic chaos of naval combat. The trigger mechanism required no moving parts that might jam or break under stress. The power supply activated automatically when the shell fired, conserving battery life during storage. And the entire system had been engineered for mass production. Simple enough to manufacture by the millions, reliable enough to trust with sailors' lives, cheap enough to fire and forget. By contrast, Japan's most advanced electronics required hand assembly by trained technicians, operated for hours before failing, and cost more than a soldier's annual salary. Nakamura had seen Japan's own attempts at proximity fuses. They were laboratory curiosities, devices that worked under controlled conditions but failed in combat. The components couldn't survive firing. The batteries died in cold air.
The circuits gave false triggers, detonating shells in empty sky or failing to fire at all. Japanese industry, stretched to its limits producing conventional weapons, couldn't spare the resources to perfect such an advanced system. And even if they could, Nakamura realized they lacked the fundamental industrial infrastructure. The Americans weren't just ahead in one technology. They were ahead in every technology that made this weapon possible. Advanced vacuum tube manufacturing, precision wire drawing, miniaturized battery chemistry, radio frequency design, quality control systems that ensured reliability across millions of units. The proximity fuse wasn't a weapon, it was a concentrated drop of American industrial might, a demonstration that the United States could afford to put a radio-guided computer inside every anti-aircraft shell and throw them away by the thousands. The psychological impact on Japanese forces had been severe and cumulative. Pilots who had trained themselves to accept death in combat, even to seek it in kamikaze operations, found themselves unraveled by deaths they couldn't anticipate or understand. A fighter pilot could steel himself to face American Hellcats, could calculate odds, could rely on skill and courage. But how did one face shells that exploded at the perfect moment without human intervention? The proximity fuse removed the element of chance that allowed warriors to maintain hope. Traditional anti-aircraft fire created a probability field, dangerous but navigable with luck and skill.
The proximity fuse created a kill zone of near certainty. Planes that entered range of American ships equipped with VT-fused ammunition didn't dodge through incoming fire, they simply died. The impersonality of it gnawed at morale. Pilots reported feeling hunted by something inhuman, something that didn't miss or hesitate or suffer from fear or fatigue. American gunners might grow tired, might lose concentration, might make mistakes. The fuses never did. They waited patiently inside their shells, inactive and harmless until the moment of firing, then executed their single purpose with mechanical perfection. For Japanese naval aviators already facing fuel shortages, aircraft shortages, and pilot shortages, the proximity fuse represented one more technological gap they couldn't bridge. One more way the Americans could kill them at distances and with precision that Japan couldn't match. The strategic implications extended far beyond individual air battles. By early 1945, American naval task forces moved across the Pacific with near impunity. Japanese commanders planning attacks against American carriers knew their strike aircraft would face a defensive gauntlet that destroyed 70 to 80% of attackers before they reached their targets. This made conventional airstrikes militarily futile, sending 100 planes to achieve what might have required 20 a year earlier, except Japan no longer had 100 planes to spare. The proximity fuse had fundamentally altered the calculus of naval warfare. It transformed aircraft carriers from vulnerable targets requiring careful protection into floating fortresses surrounded by nearly impenetrable defensive bubbles. Kamikaze tactics, developed partly in response to the impossibility of conventional attacks, proved only marginally more effective.
Suicide pilots committed to flying straight into ships discovered that commitment alone couldn't overcome physics. The proximity fuse didn't care about the pilot's determination. A kamikaze aircraft was simply a target, and the shell exploded beside it with the same mechanical indifference it showed to conventional bombers. Japanese forces watching kamikaze waves disintegrate before reaching their targets felt the despair of soldiers who had sacrificed their last advantage, willingness to die, and found it insufficient. What did courage matter against an enemy whose bullets contained more intelligence than your most advanced bombers? Nakamura's team had documented all of this in their reports to Naval General Staff. They had included photographs, diagrams, chemical analyses, and frank assessments of Japan's inability to produce similar weapons. The final report, submitted in April 1945, concluded with a section Nakamura had written himself, working late into the night while American bombers turned Tokyo into an inferno. He wrote about the symbolic significance of the proximity fuse as a weapon that encapsulated everything wrong with Japan's strategic position. The fuse represented an enemy that could afford to be wasteful, throwing away sophisticated electronics with each shell, while Japan struggled to produce enough vacuum tubes for its radar stations. It represented an enemy with surplus to experiment, investing billions in research programs that might fail, while Japan could barely maintain its existing weapon systems. It represented an enemy that planned for the long term, developing weapons that wouldn't see combat until years after their conception, while Japan lurched from crisis to crisis with stopgap solutions. Most of all, it represented an industrial capacity so vast that it could produce precision electronics as disposable ammunition. The Americans weren't just fighting with better weapons. They were fighting from a different economic universe, one where abundance rather than scarcity defined the limits of war production.
The fragments on Nakamura's examination table had become a kind of shrine, visited by senior naval officers who wanted to see for themselves what they were facing. Admiral Yugaki Matome, commander of the 5th Air Fleet, had stood over the table in March 1945, studying the components in silence. Nakamura had explained the principles, demonstrated how the circuits worked, traced the flow of electrons through the tiny vacuum tubes. Yugaki had listened without interruption, then asked a single question: "Can we build this?" Nakamura had taken a breath before answering truthfully. "Not in quantities that would matter, Admiral. Even if we devoted our entire electronics industry to producing proximity fuses, we might manufacture a few thousand units per month. The Americans are firing hundreds of thousands. By the time we had a production system in place, the war would be over." Yugaki had nodded slowly, his face showing no emotion, then turned and left without another word. Nakamura heard later that the admiral had returned to his headquarters and ordered his remaining pilots to focus on night attacks and low-altitude approaches, tactics that might minimize exposure to American anti-aircraft fire. But they both knew it wouldn't matter. The proximity fuse was simply the most visible symbol of a disparity that existed across every dimension of the war. Japan was fighting with the tools of 1940 against an enemy whose industrial base had evolved to 1945 and beyond.
The American development program that created the proximity fuse had been one of the war's most closely guarded secrets, parallel in security classification to the Manhattan Project, and considered by some military analysts to be equally important. The program had begun in 1940 when British scientists, desperate to counter German bomber raids, approached American researchers with the concept. British industry, already stretched to breaking point, couldn't manufacture such a device at scale. But American research institutions, operating with government funding that would eventually exceed $800 million, embraced the challenge. Teams at Johns Hopkins University, Carnegie Institution, and the National Bureau of Standards worked on parallel designs. They solved problems that had seemed insurmountable. Vacuum tubes that could survive 50,000 G acceleration, batteries that functioned in sub-zero temperatures, oscillators that maintained frequency during high-speed rotation, safety systems that prevented premature detonation. By 1942, they had working prototypes. By 1943, production lines were delivering 20,000 units per day. The scale was staggering. Over 22 million proximity-fused shells produced by war's end, each one a small miracle of miniaturization and rugged design, each one disposable. The American military had debated whether to use the weapon at all, fearing that a dud shell falling into enemy hands would reveal the technology. They restricted its use to naval warfare, where duds would fall into the ocean, until late 1944, when the technology's advantage outweighed security concerns. By then, American industry was producing fuses faster than the military could fire them. The production line itself was a weapon, proof that American factories could manufacture complexity at scale. Japanese engineers examining the fragments understood this industrial story without needing to read American documents. The manufacturing quality visible in each component told the tale. The vacuum tubes had been produced by automated machinery, not hand-assembled. You could see it in the perfect consistency of the welds, the precise spacing of the filaments. The wire coils had been wound by machines that measured tension and spacing to tolerances of micrometers. The circuit boards had been printed, not hand-wired, using photographic processes that allowed identical reproduction. Even the shell casing itself, the brass housing that contained all the electronics, showed signs of advanced metallurgy and precision machining. Every aspect of the proximity fuse revealed an industrial system optimized for mass production of complex devices. Japan's workshops still relied heavily on skilled craftsmen performing operations by hand, guided by experience and judgment. American factories relied on machines performing operations by programmed instruction, guided by measurement and specification. The difference wasn't just technological, it was philosophical. American industry had learned to encode knowledge into machines, allowing rapid scaling of production without dependence on individual skill. Japanese industry remained dependent on master craftsmen whose expertise couldn't be easily replicated or expanded. When the war destroyed Japanese factories and killed Japanese workers, it destroyed knowledge that couldn't be replaced. When the war destroyed American factories, Americans built larger ones.
The emotional weight of this realization had settled over Nakamura's laboratory like a physical presence in those final months of the war. His team continued their work, documenting everything, writing detailed reports that analyzed every aspect of the proximity fuse's design and manufacture. But they knew their work had no practical application. Japan would never close this technological gap, not in the time remaining, possibly not in a generation. They were archaeologists, studying artifacts from a superior civilization, trying to understand how far behind they had fallen. Some of the younger engineers had broken down during late-night sessions, overwhelmed by the futility of their task. Nakamura had let them grieve. He understood. They were mourning not just the coming defeat, but the revelation of how complete that defeat had been from the beginning. Japan had challenged a nation that could put radios inside bullets, that treated sophisticated electronics as disposable munitions, that operated production systems Japan couldn't replicate in a decade of peace. The proximity fuse wasn't just a weapon. It was a message from an industrial future Japan had failed to reach, and the message was unambiguous. You never had a chance. Outside the laboratory, Japan burned. Incendiary raids had reduced Tokyo, Osaka, Nagoya, and Kobe to ash. The combined fleet, once the pride of the empire, rusted at the bottom of the Pacific. Aircraft that should have defended the home islands sat useless on airfields, grounded by fuel shortages and pilot losses. The proximity fuse had contributed to this catastrophe, but it was only one weapon among hundreds. American submarines that starved Japan of resources, long-range bombers that turned cities into furnaces, carrier task forces that appeared and vanished across the Pacific like chess pieces on a board too vast for Japan to control. Behind every weapon stood the same industrial system that had produced the proximity fuse, a system that measured its output in continents, not islands, that counted its workers in millions, not thousands, that treated innovation as an assembly line product rather than an artisan craft. Nakamura had tried to explain this to senior officers who visited the laboratory, hoping to understand why their planes kept falling from the sky. He showed them the fragments, explained the principles, traced the manufacturing signatures visible in each component. But what he really wanted them to see was the gap, not just in technology, but in the fundamental nature of industrial societies. America and Japan weren't fighting the same kind of war. America was fighting an industrial war of attrition, where victory went to the side that could produce more, faster, better. Japan was fighting a spiritual war of determination, where victory went to the side with more courage. The proximity fuse proved that courage couldn't overcome production capacity. In the years after the war, Nakamura would write a memoir about his time examining American weapon technology. The chapter on the proximity fuse would become required reading at Japanese engineering schools, studied not for its technical content, but for its analysis of industrial philosophy. Nakamura argued that Japan's defeat had been inevitable from the moment it challenged a nation whose approach to manufacturing differed fundamentally from its own. Japan treated weapons production as an extension of traditional craft, skilled workers making quality products, each one carefully assembled, refined through experience and intuition. America treated weapons production as an engineering problem, designed for manufacture, optimize for scaling, automate everything possible, measure everything measurable. Japanese industry could produce excellent weapons in small quantities. American industry could produce good enough weapons in overwhelming quantities, then iterate toward excellence while maintaining volume. In a short war, Japanese craft might have prevailed. In a long war of attrition, American mass production was unbeatable. The proximity fuse embodied this difference. It wasn't the best possible proximity fuse. Engineers would identify numerous improvements after the war. It was the best proximity fuse that could be manufactured by the millions with wartime resources, and that distinction made all the difference. Japan had spent the war chasing perfection it couldn't afford. America had spent the war building abundance it could waste. The fragments on the examination table had remained in Nakamura's laboratory until August 15, 1945, when the Emperor's radio broadcast announced surrender. Nakamura had been standing at his workbench holding a magnifying glass over a particularly well-preserved vacuum tube when the announcement came through the building's speakers. He had set down the glass carefully and sat in silence, listening to the Emperor's voice explain that the war situation had developed not necessarily to Japan's advantage. After the broadcast ended, Nakamura had looked at the fragments one final time. They seemed different somehow, transformed from enemy weapons to mere artifacts, relics of a conflict that had ended. But the truth they represented remained unchanged. Somewhere in America, factories that had produced these fuses by the millions were probably already retooling for peacetime production, applying their expertise in miniaturization and mass production to radios, televisions, computers, devices that would define the post-war world. And Japan would have to learn from scratch how to build that kind of industrial system. How to organize knowledge and labor and capital into machines that made products. The proximity fuse would be a teacher in that education, a preserved example of what was possible when a nation aligned its industrial capacity towards a single purpose. Japanese engineers would study these fragments for decades, reverse engineering not just the device, but the manufacturing philosophy that created it.
The symbolic weight of the proximity fuse extended beyond its technical achievement. In Japanese military culture, where warrior spirit and sacrifice held supreme value, the fuse represented the opposite philosophy: victory through abundance rather than courage, through spending rather than sacrificing. American sailors firing proximity-fused shells didn't need to be braver or more skilled than their Japanese counterparts. They just needed to have better ammunition. The weapon removed human factors from combat, reduced battle to a contest of industrial capacity. This violated something fundamental in Japanese military thought, which held that spirit could overcome material disadvantage, that determination mattered more than resources.
Kamikaze pilots had embodied this belief. Young men using their bodies as weapons because Japan couldn't produce weapons as sophisticated as their enemies. But the proximity fuse had killed them anyway, indifferent to their sacrifice, mechanical in its efficiency. It proved what Japanese commanders had refused to believe, that spirit couldn't overcome material reality, that courage was necessary but insufficient, that will couldn't replace industrial capacity. The lesson was bitter but clear. Wars between industrial nations were won by factories, not warriors. Production capacity mattered more than tactical brilliance. Engineering triumphed over valor. The proximity fuse had been, in the end, a teacher wrapped in brass and death. It taught Japanese forces that they were fighting an enemy whose industrial base operated on a different plane. It taught military planners that technological gaps couldn't be closed during wartime if they reflected fundamental differences in industrial organization. It taught engineers like Nakamura that excellence in craft wasn't enough. You needed excellence in systems, in processes, in the ability to turn ideas into products at scale. These lessons would shape Japan's post-war reconstruction, influencing how Japanese companies approached manufacturing, quality control, and continuous improvement. The nation that had lost the war of production would become a manufacturing powerhouse, applying lessons learned from studying weapons like the proximity fuse. But in March 1945, standing in his laboratory, surrounded by fragments of American technology, Nakamura had seen only the wreckage of Japanese illusions. Each tiny vacuum tube, each coil of copper wire, each circuit board represented something Japan couldn't match. The fragments were evidence, undeniable and physical, that the war had been lost before it began. Not on battlefields or in command decisions, but in factories and research labs, in industrial systems and manufacturing philosophies, in the unglamorous work of turning ideas into products at scale. August 1945. The fragments remained on the examination table, now just historical curiosities, evidence of a completed catastrophe. Nakamura would pack them carefully into wooden boxes, labeling each component, writing detailed descriptions of their function and significance. They would eventually find their way to Japanese war museums and engineering schools, studied by generations trying to understand how their nation had lost their war. But their most important lesson wouldn't be technical. The proximity fuse taught that abundance mattered, that the ability to throw away sophistication by the shell load represented power more decisive than any single brilliant weapon. It taught that mass production was itself a strategic capability, perhaps the most important one. It taught that industrial systems, not just individual products, determined victory. And it taught these lessons through the most visceral pedagogy imaginable, through Japanese pilots exploding in midair, through kamikaze aircraft disintegrating before reaching their targets, through the simple mechanical fact of American shells that thought faster than human reflexes. The fragments on the table held all this history. They were tombstones for Japanese aviators and epitaphs for Japanese industry. They were proof that courage without capacity was just elaborate suicide, that will without means was just wishful thinking. They were small, precise, beautifully engineered monuments to the power of industrial abundance and to the futility of fighting against it with nothing but spirit and sacrifice.